Welcome back. This is an Aleks training video on calculating pressure, volume, work. So work is the movement of an object against some force that's acting against it. Okay, so if you have your wrestler that you're wrestling against is trying to pin you down and you're forcing yourself up from the floor, you're doing work because there's a force acting on one way. Or if you are arm wrestling with someone and you're moving your arm down while he's trying to make it go up, then you're doing work. If you're lifting a barbell over your head so that there's a force acting down and you're pushing it up, you're doing work. So this happens in chemistry all the time, especially when it comes to gases, because gases can change several things. It can change volumes, it can change pressures, and it can change temperatures. And as it does these things, as it changes from one thing into another, it can do work on the environment. So for instance, a little cloud can turn into a huge cloud. Well, what's it done? It's shoved into the environment, and that environment it has a pressure on it. There's a pressure on the cloud to keep it small, but if the conditions are right, that cloud can do work on the environment and the cloud becomes bigger. Or if the pressure in the air is high enough, it will squeeze that cloud into nothing, and then you have a beautiful blue sky. That's high pressure. High pressure, there's not any room for clouds because it's squeezing the water vapor in the air down to nothing. Okay, so work is the ability to resist some force against you. So here's an example of that happening with a gas. A mixture of helium and oxygen gas is expanded from a volume of 56 liters to a volume of 75 liters. Okay, so the gas has gotten bigger, the cloud has gotten bigger, and it's resisting the pressure that the environment is pushing on that gas. So it's done work on the system. It's done work on the environment. So the amount of energy that it has is smaller at the end because it's exerted its energy on doing work on the system. So the amount of joules of energy that it has drops if it does work on the system. If work is done on the system, on you by the system, then your joules have gone up. But if you've expended your energy on doing work on the system, then your joules will drop. All right. Now, like I said, temperature has a play in this. Temperature, pressure has an effect in this. And volume has a pressure in this. So you're going to have to be given specific things. Let me first of all give you a definition that you're going to have to use for any of these type of problems. And that is work is going to be equal to minus pressure times the change in volume. Okay, so whatever work is being done is the drop in pressure times whatever the volume change is. Okay, so whatever the difference in pressure times volume is. So PV is work. All right, so because if you're thinking of a gas pushing against the gases in the air, well, as the volume gets higher and the pressure is harder to exert against, you've done work on that. That's what's happened. You've pushed out and the barbell has gone over your head. You've exerted a pressure, and the volume is essentially the distance over which the volume of the gas getting bigger is just like you putting your arms over your head. It's bigger at the end. It's farther away from the floor than it used to be. All right, so this formula you're going to use. It says that the pressure is held constant at 58 atmospheres, so I like that. So we've got W equals minus 58.0 atmospheres. The change in temperature, okay, change in volume, is going to be equal to the final volume minus the initial volume. Okay, so whatever the final volume is minus whatever it started to be, that's going to be your change in volume. So what is its final volume? it went to 75. So 75 minus its initial volume was 56. Okay, and this is liters. So I can rewrite that as 58.0 atmospheres times, what is that, 19.0 liters. All right, so when you do the math here, I'm not going to do significant figures yet because this is not my final answer. If it were my final answer, I would, but I'm going to do a little bit more math, so I'm just going to keep it long. So I've got work equals minus 1102. That's probably enough. 1102.0, and then it's going to be liters times atmospheres. Okay, liters times atmospheres is one way to express gases. Volume times a pressure is going to equal some temperature, and so you can express things in terms of liters and atmospheres. A lot of times work, though, is considered how much energy did it take you to exert that work, and so you're going to be answering it in terms of work and energy, which is the joules. All right, so that means that you are going to have to use a gas constant. And a gas constant will be given to you. It's in the book. It's in the back of the book. A gas constant is when we use PV equals nRT, the combined gas law, which is saying that pressure times volume equals the number of moles times the Kelvin temperature. And then if you were to divide N and divide T, this R is going to make everything work. So if you are in liters, okay, liters and atmospheres, and you divide by numbers of moles and Kelvin temperatures, your R is going to be a certain number. It's going to be 0.0820574. Okay, I usually just 0.0821, but this is its longer usage. So if you're in liters and atmospheres, R is going to equal, this is for liters, atmospheres, kelvins, and moles. So kelvins on the bottom, moles on the bottom. So liter atmospheres over Kelvin moles. This is the R for liter atmospheres. If you're, instead of atmospheres, you are in pascals, okay, which is a different unit of pressure, then you're going to say, so instead of atmospheres as pascals, you're going to have R is equal to 8.31446, and this will be either pascals or, in this case, joules. It'll be the same. Joules over moles, kelvins. Okay. So what we're going to do is we have liter atmospheres. These two R's are going to be the same. This is the same value either way, depending on what units you have. So these two things are equal to each other. So I can set this up as a conversion factor, and I can get rid of liters atmospheres by putting this number on the bottom. So this is going to be 0.0820574 liter atmospheres Kelvin moles, and then we need the other one on the other side so that they're equal to each other. So this is going to be 8.31446 joules times moles kelvins. Okay. So what'll happen is my liters will cancel, my atmospheres will cancel, kelvins will cancel, moles will cancel, and my answer will be in joules. Okay. So these two numbers I'll supply for you. I'll put them on the board or on the wall or something, depending of them. As you use them, you'll remember them. You'll remember them as you use them. Okay, so that means I need to multiply and then divide. So I've got 1102 times 8.311446 equals, divided by 0.0820574 equals, and I have W equals minus 1.116195918. I'll round this in a minute, times 10 to the 5. Okay. All right, and so I need to round now to how many significant digits. I've got 3 significant digits here, 3 here, 3 here. So I'm going to round this to 3 significant digits. So work is equal to negative 1.12 times 10 to the 5 joules. Okay, because everything else would have canceled. This is an okay answer. Normally, if you have something into the 100,000s joules, it's easier to express something in kilojoules. That's a unit that's a little, so that you don't have huge numbers. That's the whole point of having a unit. You want a unit to where the numbers are kind of workable. So this is probably best in kilojoules. So I'm going to say that in 1 kilojoule there are 1,000 joules. Okay, 1,000 is going to these 3's are going to cut with these 3's, leaving 2. And so I have 1.12 times 10 to the 2. Well, 10 to the 2 is just two dashes. So you're going to end up with work equals minus 112 kilojoules. Now, the last thing before you turn this in is you're going to check your sign. If this gas did a work on the environment, then it's losing energy, and it'll be negative. If the environment did work on it by squishing it together and compressing it and making it harder like a spring, then it will be a positive work. Okay, but this will be a negative work. It exerted work, so it'll be a negative quantity. So your answer is going to be work equals negative 112 kilojoules. Hard. I'll help you.